This is the video for Mary Beth Price textbook. This is chapter 4, and again this is from the 5th edition. Attribute data. And the most important aspect of this chapter is what is a table, or at least at this point in the lecture. This is a table directly out of GIS, ArcGIS. As a title of the table, each of these are fields. Field definitions control the type of data that can be stored in a field. You can make sure that only whole numbers or only negative numbers, specific numbers show up, or specific letters. It can be very specific. And each field is specifically defined and established before any data can be entered. Once you create the field is pretty much stuck the way it is. You cannot change it. If you go to change it, you're better off just adding a new field. You won't be able to do many changes to it. And each row is a record, as indicated by this records symbol. Now that's some terminology. Types of tables. There's an attribute table that stores the attributes of the map features, and it's associated with a spatial data layer, and it has specific fields for spatial information, such as the shape. A standalone table stores any tabular data. It's not associated with any spatial data, and that has an OID instead of an FID. And we'll get into the OID and the FIDs a little bit later. But it is important to know that a standalone table does not have any associated spatial data. These tables are made by database management systems. They're dedicated systems for managing tables of data. Essentially, we're working with completely databases. Even though sometimes it looks like Excel, they are databases. Provide data management for energy agencies, universities, companies, etc. And they're designed for multi-user environments with enhanced security needs. Focus on data tables with tools for queries, reporting, graphing, etc. A flat file DBMS, or database management system, stores data as rows of information in files. It's very simple and robust. However, it is inefficient for searching and querying. A hierarchical database management system stores data in multiple tables. Tables have defined parent-child relationships. There's a preset hierarchy of table relationships designed for specific queries. This is very efficient for specific querying. And the range of queries is limited by the structure. Relational database management system still stores data in multiple tables. The relationships are defined as needed, and they are very flexible. And they're ideal for open-ended applications when queries are not known beforehand. And these are the most common type used in GIS applications. We use Relational DBMS, Database Management Systems. Performing queries on tables. What is a query? A query extracts certain records from a table based on a specific condition, such as how many students have a GPA of 3.5, or you would say select all students who have a GPA of 3.5. How many states have a population of 1 million? You would query states with a population greater than 1 million, and you would get all of them selected for you. How many counties had a greater population in 1990 than in 2000? And then you're querying 2 different years. How many customers have last names beginning with Mac or MC? Additional queries that can be performed. SQL or SQL, many databases use special query language called structured query language. You can write queries that work in multiple database management system environments. And these queries can be saved and reused, and they're nearly always case sensitive. Here are some SQL query examples, and we will use these quite extensively in GIS 3.11. Some examples on the right: select from cities where the population in 1990 is greater than or equal to 500,000 people. Another one: select from counties where beef cow underscore 92 is less than beef cow underscore 87. That sounds like the number of beef cows in 92 versus those in 87. And you can add to it. Select from parcels where the land use code is equal to 42 and also that their value is greater than 500. Select from rentals, which is the name of the item, where rent is greater than $700 and the rent is less than $1,500. In most databases, SQL expressions are case sensitive. This one here, Smith does not equal Smith. Multiple criteria queries. Multiple criteria queries using and or, such as state equals Alabama or state equals Texas. That would pull up all those that have a state of Alabama or a state of Texas listed. Notice that the field name must be repeated for each condition. We have state equals Alabama or state equals Texas. We cannot say state equals Alabama or Texas. It doesn't work. We need to repeat the field name. Value is greater than 5,000 and the value is less than 10,000, which would give us a figure between 5,000 and 10,000. Searching for partial matches. Sometimes you need to find one string within another rather than exact match. Find all customer names beginning with MAC or MC. Find all zip codes beginning with 0. Typically, you use a wildcard character, such as anything, MAC, anything, or anything, MC, anything. And again, with the 0, it would give us 0, and then any number afterwards is appropriate for our query, for our search. Using the like operator, using a query such as name like %d% finds all the Democrats. The % key is the wildcard, and it ignores things like Don or Danforth. Try to figure out the reasoning behind that. In this case, we have a parenthesis before and after the D. Therefore, Don doesn't count because there are no parentheses. Similar to finding New Hampshire, using %new space %, we would find New Hampshire, New York, but not Newcastle or Kennewick, because there is no space after the word new in these two words. Results. The result of a query is a set of selected records that meet the criteria. Subsequent operations on the table will use only the selected records and ignore the others. For example, you may export the selected records to a new table, calculate statistics on the selected records, calculate new values for the selected records and insert them in a new field, produce a report based on the selected records, or export the selected records to a new shapefile. We do all of these in GIS 3.11. Joining and relating tables. To join tables, we have a destination table and a source table. and each must have a common field. In this case, FIPS matches FIPS. And then in the join table, with them joined, we also have an FIPS. Join facts. Joins are temporary relationships between tables used by a relational database system. Tables must share a common field or a key field, and it treats the two tables as a single table. The original stored data is not affected, and the join can be removed when it's no longer needed. One-to-one joins. Destination table, and we're going to always imagine this one on the left, and then a source table always on the right. When each record in the destination table matches exactly one record in the source table, we call it a cardinality of 1-to-1. And in this case, we have the state matching up with the state, and we have one in Washington and one in Washington. That's a 1-to-1. There are multiple types of cardinality. There's a 1-to-1. Each state has one governor. Each husband has one wife. One-to-many. There are many cities in a state, and there are many schools in a district. A many-to-one is many cities to states. Again, the destination is on the left, and many schools to districts. And make it even further complicated, there is a many-to-many. There's many students in many classes, and there are many stores for many customers. In evaluating cardinality, we'll always put the destination table first. Rules of joining. Each record in the destination table must match one and only one record in the source table. This is a 1-to-1. In a many-to-one, with the destination table on the left, there are 4 instances of Washington, but only 1 instance of Washington in the source table. That's a many-to-one. Because there are many counties in each single state. A one-to-many. We cannot have a one-to-many because it violates the rule of joining. A record to join the destination is ambiguous. We must use a relate instead, because the destination table cannot have these multiple items. A relate is it's similar to a join, except the tables remain separate. Items selected in one table may be highlighted in the related table. I'll tell you right now, we do not use relates in GIS 311. We only use joins, and we use joins a lot, but we never bother with relates in this course. In related tables, select the New England states. The subregion, New England, New England, New England, New England, then has a bunch of additional items on the right. And this is to help us, for example, find the representatives of New England states. Summary statistics. And this is after you've already done a query. Statistics on a table field. Based on values in a field, and it includes all records or a subset based on a query. So you would do a query, and notice in the background here we see some things are selected light blue, and then running statistics, it would only take or consider statistics on these light blue items. If there are none selected, then you could do it based on all the records. And in this case, it's a simple right-click statistics on this population 2010 field that you see behind here. And also over here when you see the statistics. This is done first, and then this information pops up. And notice the count. There must be 2 that aren't showing, because this is 4 showing over here. But this is what we call statistics on a table field. Summarizing tables. This calculates statistics for a group of features in a table. It groups by unique values in the one field. The user chooses the statistics to calculate for other fields. It produces another table as output with groups and stats. It answers such questions as how many people live in each subregion and what is the total area of each subregion. We actually do not do much summarizing in GIS 3.11. Nonetheless, how do you summarize? You right-click a subregion field, choose the statistics, and you name the output table. We'll get to that in other courses. The summarize output table, the count field is always generated automatically, and this is an output table, summarize output table. Again, we won't be using these in 3.11. Could we now draw a map of deaths by state? There are no features, and this is a standalone table. And therefore, there's no, because there are no features. Joining the table, we have a states layer and a summarized table. The value is the sum of the population in 2010. We are not normalizing. We'll learn about normalization later in the course. We chose a color ramp of nearly white to dark green and create a map based on the summarized table. Database storage concepts. Fields. Fields have specific types available. They must be defined before they are used, and once they're defined, they cannot be changed. Some of the rules for naming fields: they be no more than 13 characters, only letters and numbers, as we've been talking about, and it must always start with a letter, which is why in this course I've instructed you to never start with a number, never have spaces, and only use letters and numbers. Binary data, and this is detailed, and it's not imperative that you can conceptualize this, but it's good to know. It's the fundamental mode of computer storage, and that's why it can be so fast. Data are stored in a series of zeros and ones, and they're represented numbers in base 2 bits. Bits are grouped by 8 to form 1 byte, and a megabyte is 1,000,000 bytes. Here we have 8 bits, so it makes 1 byte. Notice 1 bit, 2 bit, 3, 4, 5, 6, 7, 8. ASCII storage. It's the American Standard Code for Information Interchange, ASCII, ASCII. It stores letters, characters, and symbols as single 7-bit binary codes. Some more storing data. Text is always stored in ASCII format. Numeric data may be stored in ASCII or binary format, and generally binary is more efficient. ASCII stores 3-letter codes of 1 byte each, which means 3 bytes. Therefore, 106 would equal 49, 48, and 54, and therefore this long number. Binary stores 106 as a single 1 byte binary number. It would equal this number right here. Therefore, it is much more efficient to use binary storage for the computer. Storage limits. A single byte can store value from 0 to 2 to the 8th power minus 1. Larger numbers require more bytes. 1 byte, 2 to the 8 minus 1 is 255. 2 bytes, 2 to the 16th, etc., etc. Signed numbers require a bit to store positive or negative, so the storage limits are smaller. And again, this is a little bit beyond where we need to go technically, but it is good information to brush over. Integer versus float storage. The scientific notation of 3.2957239 times 10 to the fourth. Binary stores whole numbers, or integers. To store decimal values, the computer stores a form of scientific notation with a mantissa and an exponent, as shown below. Float precision. Large numbers start to lose precision because the number of significant digits in the mantissa is limited. A double precision floating point allots more storage to the mantissa value, but that also, of course, takes up more storage. Database storage. Database fields are typically defined by ASCII versus binary, bytes of storage allocated, and an integer versus a floating point. Definition limits the values that can be stored. It is important to match the type to storage requirements. Try to minimize storage space while making sure all potential values will fit in the field. The text field with 10 bytes misses SIP. Binary 2 bytes signed integer negative 32,767 to positive 32,767. Single precision floating point, we have that long monstrosity. This is a helpful graphic to use when you're completing the homework for chapters 2, 3, and 4. A short, long, float, double, text, date, and blob. These are all field data types that we'll use in GIS 311. At times, I will tell you need to choose a double, or choose a short, or choose a float, and other times you'll choose on your own. What kind of storage would be used to store the following kinds of data? How many bytes are needed for each? Somebody's last name, number of children in a household, student grade point average, year of birth, and county population. Something to think about. I can tell you the first one, last name, it would be text because that is a text character. Number of children in a household, that's always a whole number. So that was easy to figure out. Think about those and see if you can come up with the answers. About ArcGIS. Working with tables. Tables contain attribute data. There are many formats with one interface. Tables may come from DBase files, info files, ASCII text files, records from SQL database systems, and specifically we'll be using Excel worksheets. We'll use some DBase, but for the most part Excel worksheets. Here's another table interface. We've already talked about the field, the record, the title. There is a status bar telling us how many are selected, and then a right click in the field name, you get a menu. That's always a good thing to try, is try the right click in the field name, and then also head up to the options menu, which is a drop down. You can see the little down arrow. When managing multiple tables, there are ways to switch between them. This one right here is tabbed. You could choose this tab or this tab, or you can create a vertical group to spread them out. In this slide, we have the table options menu. In this case, we have two tables side by side, and this is the active one, and then the table options menu was activated, and they put it over here to give you a little bit better look. These are all the options that you'll get from the table options menu, and all of these commands would affect only the active table. You cannot do the function on both tables. Adjusting field width doesn't change the stored file, it just affects what you can view. Just hover over it, you'll get this funny looking arrow, and you can click and drag. Very simple. The Field Properties tab. This I don't use myself all that often, but you can use to show or hide all, move a field up or down, hide a field by unchecking it. It tells you the field alias, and then you can also look at the format. We will be changing the format to make our numbers look more appropriate. There's a shortcut to field properties. You right click, go to the field name, and click Properties, and you'll get the field properties. We'll do that every single lab, multiple times. Formatting the field display. In this case, we're going to the number format. We're choosing numeric, and instead of this blob of numbers, we're going to change POP 2010 to show the commas to separate the thousands characters. It just makes it a lot easier for the viewer once it's on the map, because we'll pull this data into our maps. Table appearance. We'll use this color for selected records. We'll always keep that light blue so that's all the same, but you can choose many other different appearance options for your table. Sorting tables. If I wanted to sort by name, I would just click Sort Ascending, Sort Descending, or choose Advanced Sorting. And you'll notice that a lot of things are right click. Right click here, here, here. Right clicking is something we do all the time. Select by attributes. Some valid queries. Select where population of 1990 is greater than 1 million. State name equals Alabama. Population in 2000 is greater than or equal to the population in 1990. Database tables have field names enclosed in quotes. Geodatabase tables have field names enclosed in brackets. In this case, the whole purpose of the slide is to show when you have 34 items selected, there will be this light blue. There'll be light blue in the table, and there'll be light blue in the map area. And in this case, they've selected Show Only Selected Tables so that none of these white lines appear. Over here, it's saying Show All the Tables, and that graphic actually depicts that. We'll use that every single lab. Clearing selection. After you've used your selected tables, selected fields, rows, you will click the Clear Selection button, which is right there, or right here, or right there. Multiple ways to do things. Field data types, you've already seen that. I'll skip through it. Adding a field. Once you're in a table, you go to this Options button and add a field. From there, you'll choose the name. Remember the naming conventions. What kind of field, and some specifics. Think about the field type before you add the field. If you're going to add multiple fields, it's easier in the catalog properties. We're not going to do that, so I'm going to skip over that slide. Editing and calculating fields, something we also do almost every single lab, starting with lab 5. So 5, 6, 7, and 8. We start editing by opening the editor toolbar, and then we can go in and actually edit the items. Then you would save editing. Calculating fields, add a new field if necessary, and consider whether you need decimal places when you add the field, and that would be as you choose the type. And then you would calculate your field. You would go down to Field Calculator, which I suspect they're going to show us on the next slide. Yes. Once you go down to Field Calculator, you'll get the Field Calculator window. You enter the the expression. In this case, we're taking Hispanic divided by population in 2000 multiplied by 100. Usually the field should be empty, and of course it's a new field, and calculations cannot be undone unless you're in an edit session, which is why they often suggest to go into an edit session before you do any calculating. Geodatabase geometry measures. We will not be getting into Geodatabase, but these are automatically created and maintained, and that's an important answer for some of your homework. They usually appear at the end of the table, and that's shape area field and shape length field. Units will match the units of the coordinate system, which we'll also get into a little bit later. Some more geometry measures. Shapefiles do not create or maintain area or length fields automatically. They must be created and updated manually. So we're talking about area, for example. If we were to clip out some portion of a field or some portion of a shapefile, it wouldn't keep the area statistics correct for us. And just as they're showing on the bottom here, if you find an area field, there's no guarantee that is correct. I never trust an area field. I always create my own area fields, and we'll actually do that in some of the labs. Be careful. Area, length, and perimeter fields in the shapefile are not updated when features change. Now, in this case, some of these figures would actually come out to be identical across the shapefile instead of combining them. Or you'll get one figure from one portion of this when we merge them, or we dissolve in this case, and the numbers are going to be inaccurate. And we'll see that more once we get into making maps. User geometry calculations. Right-click an empty or incorrect field to update, and then you calculate geometry. And in this case, after creating this shapefile here, we would create a new field, call it area acres 2, and then update by doing calculate geometry. And in this case, we would choose the area, and also we'd have to choose a coordinate system. Test yourself. A field named area in a shapefile will always have the correct area. False. We just talked about that. A field named area in a geodatabase will always have the correct area. In this case, it says false. Automatically updated fields in a geodatabase are called shape area. So therefore, the trick is in the name of the area. How to join or relate tables. You right-click on the destination in the table of contents. We always start with the destination, where all of the stuff is going to. From there, after a right-click, we say joins and relates, just as it's showing down here, and then choose join. And then we get this join window, and then we make our selections, which will probably be on the next slide. It is not. We'll do joining in the second lab, lab number 2, presidential politics. Importing tables. We can import ASCII tables. They are allowed in GIS. They can be tab delimited, comma delimited. What is not allowed is fixed column. So we can take this ugly looking table right here and import it, and it'll work out perfectly. And we will actually do that in lab 5. Excel files. We'll use Excel files starting in lab 2. Excel worksheets with a suitable layout can be opened as tables in ArcGIS. Most functions that do not involve changing the file will work, such as sort and query. The tables, however, cannot be changed or edited. Requirements. The first row must contain field headings with legal names as defined earlier, and those are no spaces, no funky characters, must start with a letter. That is why I'm so very specific on all of our file names and our field headings. No blank rows or formulas should be used, and each column should contain only text or only numbers. It is helpful for each column to be formatted as text, numeric, etc. And we will format our columns to be formatted a certain way before we import them. But it is important to remember to do those steps once we get to Lab 2. An ArcMap cannot open files that are already open in Excel. They must be closed first. And this is another pain that people run into. You have to remember to close Excel before you start using them in GIS. Here we have an acceptable worksheet. The sheet name is correct. There are no errors there. There is a top row that has all the field names. They're all legal. And the columns are formatted as text or numeric. We can't see that, but they're telling us that that's true. Workbooks and worksheets. An Excel workbook file, XLX or XLSX, may contain more than one worksheet. By default, there are 3, as you know, sheet 1, 2, and 3. There may be more. ArcMap can only open one worksheet at a time. You will open the workbook like a folder and then select a single worksheet. And that's important to know. You get the file, but then you choose the worksheet. And it does appear as though these are separate files when you bring it into ArcGIS. Adding a worksheet, you use the Add Data button. You open the workbook like a folder. You add the named worksheet or the first unnamed worksheet. And in this case, there are 3 sheets. In this case, there is 1 sheet. And going back to here, notice how this is a worksheet and then sheets 1, 2, and 3 are there. You must choose within this XLSX file. And notice there is an X allowed. An Excel file, you can use XY locations in a table to produce points on a map, lat and long, or latitude and longitude. For us, remember that latitude is always positive and the longitude is negative because we're going from the prime meridian. You also must know the coordinate system in which the numbers were taken so that they go in the right place. Displaying the X and Y data, use the Display X and Y Data button. This dialog opens up and you can import the data. We'll actually do that in one of our labs, Lab 5, I believe. Degrees indicate a geographic coordinate system, GCS, which stands for Geographic Coordinate System. NAD 83, North American Datum 1983, is the most common. Other tables might have units in Universal Transverse Mercator, UTM, meters, state plane feet, etc. You must know the coordinate system to create correctly located points. And here we have a map showing Oregon climate stations. Stations appear as points on the map and event layer. Export to Shapefile or feature class to keep permanently. And I've never been able to figure out exactly what they're getting at with this random slide. And I'm wondering if they even meant to include it. Here's a fancy schmancy map with, and I'm joking because it's a very basic map, but 2 layers that are in there. One from a C drive and one from a Geodatabase, which we'll talk about in a future date. And that is the conclusion of Chapter 4. If you have any questions, please feel free to email me, use the discussion boards, and I'll see you in class.